All right. Well, we will go ahead and stop early because we definitely want to take care of that. But hope everybody's doing okay today. We're going to continue with our lesson. We're talking about vectors in the plane. So just a couple of reminders. Remember, tomorrow morning is the deadline by the end of tutorials. If you have any outstanding assignments, if you want to retake, say, the exam from last week, tomorrow morning is going to be the last time to do it. I'll probably go ahead and open up the door a little earlier because it's the last day. Because tomorrow I'll go ahead and start finalizing the grades during class. You guys are going to go ahead and take the district assessment. And I do apologize. Pretty much for you, the majority of the material we have not been able to get to yet. So, it's just I've been asked to do it. We just haven't gotten there yet. So just make your best guess. It is not for a grade. Do not worry about it. Okay. It's just something we have to do. I did get some information about next week. Tuesday and Thursday are going to be the English 1 and 2 star days. So if you are done with the English star, you don't have to worry about it. Then Tuesday and Thursday are going to be late start days for you. So the bell will ring at 1:30 and the tardy bell will be at 1:35. On Tuesday, you're going to go to periods 1 through 4 in the afternoon. So I will see you on Tuesday, but this fifth period. I'm sorry, I will not see you Tuesday. On Thursday, you're going to go 5 through 8. So I'll see you first thing in the afternoon on Thursday. So yeah, basically it's an A Tuesday, B Thursday. All right. So I'm already thinking probably what we'll go ahead and do. I'll have an exit ticket over vectors in the plane. We're only going to have 30 minutes, so that would be plenty of time to go ahead and do that. We'll have a quiz next Thursday over vectors in the plane. I'll be telling you what to look over, but you can always use your notes. But that's what's happening the next couple days and next week. Say again, man? I'm sorry. I'm old. What's up? In my neck of the woods? What? So you want me to say what's happening in your neck of the woods? What's happening in your neck of the woods? Yeah. Okay. All right. Okay. There you go. All right. Well, let's see what's happening in our neck of the woods. There you go. Okay. Okay. So yesterday we were talking a little more about vectors. We've been looking at component form. Remember, that's A, B. The magnitude was the square root of A squared plus B squared. Okay, and I introduced a couple of formulas yesterday that are going to be really important to us, especially, for the exit ticket next week, the quiz. So let's say I have a vector whose magnitude is going to go, I'm going to go ahead and give it to you. Let's say a vector's magnitude is 8, and let's say it's measured from the positive x-axis. I'm just going to make one up. Let's say 17 degrees. Okay. Now, if you have these two items, if you have the magnitude and the direction, remember it has to come from standard position, the positive x-axis, we can immediately figure out component form, this form that we've been looking at all week. The formula was the magnitude times the cosine of theta, magnitude times the sine of theta. Okay. So all we have to do is just go ahead and plug in. So this one would be magnitude 8 times the cosine of 17, magnitude 8 times the sine of 17. And then it's just a matter of plugging it in the calculator, and we can go ahead and get those values. In fact, this is where we stopped yesterday on that word problem. So if I were to say 8 cosine of 17, okay, about 7.7, let's say, and then I got 8 sine of 17, so about 2.3, okay. So this would just be 7.7, 2.3. There you go. That formula will immediately give you the component form if you know the magnitude and theta measure. Now let's say we wanted to go the other direction. Okay, let's talk about that theta measure for just a second. If I have a vector and I give it to you in component form, let's say something like 3, 7. Now remember, this component form works just like a ordered pair. What quadrant would this vector be in? It'd be in the first one because both A and B are positive, right? So from the origin, I'd have to go 3 to the right, 7 up. So you're going to have a vector V that looks like that. Now, if I use that tangent formula that I showed you, but we really didn't have a chance to work with, the tangent of theta is equal to B divided by A. If I plug in the values of B and A, I'm going to be able to find the measure of rotation from the positive x-axis. Okay. Well, let's see here. If I say tangent of theta is equal to B is 7, A is 3. You guys remember, if I'm given the ratio, how do I find theta? There's something I have to do to tangent. Oh, not square root. It starts with I. Oh, not imaginary. Inverse. We have to take the inverse. So tangent inverse of 7/3 would give me theta. Well, let's see what that is. Okay. Tangent inverse of 7 divided by 3. So I know that's about 66.8 degrees. So I know this angle of rotation is about 66.8 degrees. But remember, those two formulas, this guy right here, to find the component form, the magnitude of V cosine of theta, the magnitude of V sine theta, as well as tangent of theta is equal to B divided by A. Here, to use these formulas, you have to know theta starting from the positive x-axis. You always rotate counterclockwise. Okay. All right, any questions on that? Okay, well, let's get back to what we had yesterday. We talked about a quadrant bearing, we talked about true bearing, and then I believe we were on this problem right here. Okay. So we're looking for the resultant, the one vector that's going to answer this question for me. So the vectors that were provided, let me go ahead and write this out. The resultant, what we're calling R, is equal to the two vectors we have added together. Okay. And you'll remember we used that formula that I just showed you, magnitude cosine theta, magnitude sine theta, to go ahead and get those. We just haven't found the decimal yet. Okay. So is everybody okay with what we've done so far? Now you'll notice in the problem, like the first vector, it says Tia walks north 50 degrees east for 120 feet. So we know the magnitude is 120, but somebody remind me, why are we plugging in 40 instead of the 50? There you go. Remember, just like I mentioned, that theta value that you're going to plug in for this formula, it has to start rotating from the positive x-axis. North 50 degrees east, here's north, there's east. This is what we're given. Okay, so I can't plug 50 in here. The formula depends on rotating from the x-axis. It's something really simple and small that's easy to forget. Okay. Well, let's figure out what these expressions are going to be. Okay, let's see here. So we have 120 cosine of 40, so document B. That's not what I need. 120 cosine of 40. So let's say that's about 91.9. Then we have 120 sine of 40. So 77.1. So 91.9, 77.1. Okay. So X is, I totally forgot the numbers. 91.9, 77.1. 91.9, 77.1. Y is equal to. Now we're going to do the same thing here. 80 cosine of 0. 80 cosine of 0. Okay, that's going to give me 80, and then, forgot about the 80. 80 sine of 0. So I got 0. Okay, well that one's actually really easy for me. So 80, 0. Okay. Now, in order to find the resultant, what I need to do is take these two component forms and add them up. Okay. So my resultant R is going to be 91.9, 77.1 plus 80, 0. Okay. Well, here's the thing. How do I add vectors? Yeah, there you go. Add the corresponding values. Add the A's. Add the B's. Okay, well, somebody help me out. I need 91.9 plus 80. There you go. So that's 171.9. And then 77.1 plus 0, 77.1. There you go. Remember, this is what we call the resultant. Now, in order to find the resultant magnitude and direction the ball is traveling, well, what we need to go ahead and do is find the magnitude and direction, just like I showed you of this guy right here. Everybody okay with what I've done? I found the resultant. Okay. So now I need to find the magnitude of R. Well, what was that formula for finding the magnitude? Square root A squared plus B squared. So the square root of A squared, okay, I'll go ahead and write it out, plus B squared. So this would be the square root of 171.9 squared plus B squared, 77.1 squared. Okay. Now we just need to go ahead and figure out what that is. So let's see here. Now my answer will be a little off because I'm not going to use the values here. So I'm taking control 171.9 squared plus 77.1 squared. Okay. So 188.4. Okay. So here the magnitude is the distance that she's walked. So this result, how far is she from where she initially started? Well, she's about 188.4. I think we're talking about feet here. 188.4. Is it feet or is it meters? What are we talking about? Feet. Okay, it is feet. There we go. Okay. Now the only other thing I want to do is find the direction she is. Okay. So what was the formula to help me find theta? There was one trig function I had to use. Okay, there we go. So tangent of theta equals B over A. Okay. All right. So remember, from the resultant, there's the A, there's the B. Okay, that's a B. So I'm going to say tangent of theta is equal to B, the 77.1, over A, the 171.9. But Brandon's absolutely right. Then we need to take the inverse of that. Okay. So let me go ahead and figure out what that is. So tangent inverse. Tangent inverse of, what was it? 77.1? Oh, I thought it was the 77.1 over the 1. No, we're right, yeah. Because it's always B over A. Mm-hmm. Okay. Divided by 171.9. There we go. So that means we're 24.2 degrees from the positive x-axis. Okay. But now here's where you want to be careful. Okay. Let me get back over here. If it'll let me do this. Come on. I don't know why it's doing that. So theta is about, what was it, 24.2 degrees? Now, you always want to keep your answer consistent. How was the angle originally given to me? Was it given to me as a quadrant bearing, a true bearing from the horizontal? It was a quadrant bearing, right? So take a look at this. 24.2 degrees, that actually tells me that's this right here, right? But I want to make sure that my answer is the same measurement, the same style as what the problem is given to me. So I can't say north 24.2 east because we need to know what this is right here. Does that make sense for everybody? Okay, so all I need to do is take the 24.2 and subtract from what? 90. Yeah, that's easy enough to take care of. 90 minus the 24.2, so about 65.8. Okay, all right. So while we know that she is, oh, I think I went back to the wrong page. There we go. She's 188.4 feet away. She's north 65.8 degrees east of where she was. Okay, questions? Yes. But that's okay. Remember, this is just the first problem we've seen, so we're going to have time to practice it. We'll get used to it. Okay. Let's try another one. Okay, here we go. Here's an example of golf. While playing a golf video game, Anna hits a ball 35 degrees above the horizontal at a speed of 40 miles per hour with a 5-mile-per-hour wind blowing as shown. Find the resulting speed and direction of the ball. Okay, find the resulting speed and direction. Well, what are the two vectors I'm going to use to help me find the resultant? What do they represent? Like, what's one thing that's happening here? Okay, so we're talking about the initial speed of the ball, right? So why don't we go ahead and say that the first vector is B for ball. Okay, so what's the other quantity, the other item in the problem? Now, we're not setting it up yet, but what's the other item? We're hitting the ball, but what's something that could affect the ball? The wind. The wind would be the other vector. So let's go ahead and say W is the wind vector. So in this case, in order to find my resultant R, I need to take the component form of the ball and add the component form of the wind, just like we did a moment ago. Okay, BW. All right, so now this is where that formula is going to help me out. Okay, we're going to need the magnitude times the cosine theta, magnitude, sine of theta. Okay. Now let's talk about the ball first. How hard was the ball hit? How fast is it traveling? 40 miles an hour. So that is my magnitude. So I'm going to go ahead and say 40 times the cosine of what? Now here's the thing. It says above the what? Above the horizontal. So if it says with the horizontal, that means it's already rotating with the x-axis. So in this case, I can actually plug 35 right into the problem. Bless you. So what would be the second part of the problem? 40 sine of 35. Okay. And now we'll go ahead and figure out the decimal value of that in just a second. Now, we could go ahead and do the same thing for the wind, but if it's going in a specific direction, if it's going directly north, south, east, or west, you don't actually have to use that formula. Okay. What direction is the wind blowing? East. How do I know that? We have the diagram right here, right? Now, how fast is it going? 5 miles an hour. So I can immediately say that the wind would be 50. Okay. If it's blowing in one of those four specific directions, one of your values is going to be 0. Let's just say, for argument's sake, let's say the wind was blowing due north 5 miles an hour. What would the component form look like then? Remember, think of it as an ordered pair. It would be 0, 5. If it were blowing west, then it would be -5, 0. Okay, just think of it as an ordered pair. Okay, so there you go, just like that. Okay. Is everybody okay with what I've done? So I got my two vectors. Now what do I do to them to get the result? Just add them up. Okay, so let's go ahead. Maybe we can do all this at the same time. I know that I'm going to take the A value here and combine it with the 5. That one there is going to combine with the 0. The resultant is going to be B plus W, exactly what I have here. Okay, well, let's see what the calculator says. 40 cosine of 35. Let me get rid of all this. 40 cosine 35 get out of there, and I know I'm going to have to add 5 to that. I'm just going to take care of it all at one step. So let's say 37.8. Okay. So 37.8. And then now I need to figure out the other part. 40 sine of 35. 40 sine 35. And do I really need to put the plus 0 at the end? I mean, I could, but it's not going to change anything. So that one's 22.9. You could probably even make an argument for 23. Okay. There you go. I found the resultant. Okay. Remember, if we were doing this graphically, this would be the third side of the triangle. Vector B would be one side, vector W would be a second, and then the resultant would be the third side. But remember, we're just going to do these algebraically. We're not doing them graphically. Okay. Just so, I mean, I could, but I think it's just going to take more time. If you want me to show you graphically, I will. Okay. It's just more visual than algebraic. Okay. I actually taught them both, yes. Okay. So now, what am I going to do with that vector R, the resultant? What's the question say? Find the what?
The resulting speed and
Direction of the ball. So the resulting speed, that's actually saying find what? Starts with the M. The magnitude. So this is my A, this is my B. If I want to go ahead and find the magnitude of R, it's the square root of A squared plus B squared. So that will give me the actual speed of the ball with the wind affecting it. Okay. Now for this one, why don't I go ahead, I'm going to actually use the decimal values that I have. So I'm going to go ahead and say control divide. So we have this one right here. Plug it in, squared. So this one I'm just actually using the exact value from the calculator. So my answer is going to be a little more approximate. Plus, parentheses, B squared. Whoop, went a little too far there. If it'll go down. There we go. And then I'm going to close that out, square it. Okay. So now when I push enter, how fast is the ball actually traveling? 44.2, yes. And we're talking miles per hour, right? Okay. So about 42 miles per hour. There you go. Oh, yeah. It's a Wednesday. 44.2 mph. There we go. I was just saying if you're paying attention, obviously you were. Okay. All right. Okay, so how can I find the actual direction angle? The amount it's been rotated off the x-axis. Oh, now remember, we're not looking for a quadrant bearing. There was a formula we had that gave me theta. Tangent. Remember, tangent of theta is equal to B divided by A. Once you have the resultant, you're always going to do two things with it. You're going to find the magnitude, and you'll use A and B to find theta. So tangent of theta equals, the B value is 22.9 over 37.8. Okay. And then once again, what do I got to do to tangent to get theta? Got to take tangent inverse. So let me go ahead and use the actual values here. In fact, what I'm going to do, I'm going to take the 22.9 value. I'm going to divide it by the 37.8 value. So there's the ratio of B divided by A. So now I'm going to go ahead and take the tangent inverse of that. So I'm getting about 31.3 degrees. Okay. About 31.3 degrees. I mean, I just went ahead and did that to go ahead and get a more approximate answer. But, I mean, really, let's see how far off we would be if I just plugged in 22.9 and 37.8. Did you do that? Okay, yeah, see, it's it's going to be the difference between 1/10 of a place. So I'm not worried about that. Okay. Now, let me go ahead and show you this visually. I'm not going to work through the entire problem, but let's kind of look at these vectors here. She hits the ball 35 degrees above the horizontal, right? Okay. Oh, that was weird. Let's use it. Well, let me pull this guy over here. Get a little bigger. Okay. So she hits the ball 35 degrees above the horizontal. So let's say this is the initial path of the ball. And of course, it's going to turn into a parabola eventually, but let's just say this represents the path of the ball. So this is 35 degrees, right? And we know the ball is going 40 miles per hour. Okay. Well, what direction is the wind going? The wind is going due east. How fast? 5 miles an hour. So I'm going to go ahead and draw a second vector that's much shorter, because if this one's supposed to be 40, well, this one's going to be 5, right? Okay. Well, remember what we did? I think it was last week when we did this. These are the two sides that I'm going to start a triangle with. But we can never put two terminals together. We can never put two initial together. It has to be terminal to initial, right? So I'm going to take this vector right here. Well, I'm going to move the 5 too. But I'm going to move that guy right there. So he's still 5 miles an hour, right? Now, that resultant that we've been finding, just like I said a little while ago, that is the third side of the triangle. Okay. We found the component form of this third vector right here. Okay. In fact, we know how fast is the ball traveling. Our final answer said what? Okay, 44.2. Now, why would the ball actually be traveling faster than what we hit it? There you go. You'll notice it's going 40 miles an hour, but the wind is going to play a part in increasing the speed of that ball, right? Okay. Now, theta, we originally went ahead and said that this right here was the 35 degrees, but because of the force of the wind, the effect, we know that it's only rotating 31.3 degrees. That's what we're actually finding. Does that kind of help visually to see what's happening? Okay. Yeah, now remember, we're stuck in a two-dimensional world right now. I didn't even do three-dimension vectors with Pre-Cal IS, but it's very, very similar in a three-dimensional setting as opposed to a two-dimensional, but we're just kind of limited by what we're doing. Okay. Is everybody okay with that? All right. Okay. All right, like I said, I know that's a lot of information to take in. We're going to continue to practice. Do not worry. Okay. Remember, we have no rush in here. If we need to take extra time, we're going to take extra time. Okay. All right, so let's go ahead. Why don't we say we stop for today instead of starting a new problem?